and you are well versed with the concepts, basic concepts, and whatever is remaining, we will try to clear it out. Let me just present my screen here. Okay, so this is the problem here. So on the screen, a DC machine is connected with a supply. Okay, and first read the problem very carefully. Okay, this seems to be a very long problem, but we will break it into parts by parts, so we will be able to solve it very conveniently. So I hope you are able to see my screen, right?
Sir, actually, I have a doubt. The topic of transformer from transformer.
Yeah, yeah. Go ahead. Which? Okay, okay.
Sir,
Which topic?
sir, parallel connection of transformer.
Parallel connection of transformer. Is it from the problem I given in the last session?
Yes, sir. Sir, and as assignment, sir, from the assignment.
Okay, from the assignment. So, mm, okay, let me see. From the current week's assignment, whichever you have submitted.
Yes, sir.
Okay, so what is the doubt? Please.
Sir, doubt was the regarding of this Scott connection, not parallel connection, sir.
Acha, Scott connection. So, I think I haven't taught you a Scott connection. Am I right? Okay,
Yes,
anyway.
sir.
Uh, so, okay, what is the doubt there? Please let me know. And I think at the end, if I get time, I will discuss that Scott connection. Okay. So, you just,
Just simple doubt I have.
yeah, go ahead. What is the doubt?
Uh, sir, if you will open the assignment, that will more clear.
Okay, okay. I think it will take a time because I have not logged into the that thing. So, will it be fine if we clear it at the end?
Okay, sir. Okay, sure.
Okay, thanks. So, okay, so let's focus on the problem here. Are you able to see the problem?
Yes, sir.
Okay. Okay, so I hope you have read the problem. Okay. So here it is asked that what will happen when the switch is closed. Okay. So from the figure, it is not clear whether this machine is motor or generator. Okay. And if we see from this figure, we can guess when switch was off, right, at t is equal to 0, when switch was off, the rotor must not be rotating or armature must not be rotating. Okay. So at that time, your induced EMF will be zero when your rotor is not rotating, and you have connected your switch at t is equal to zero. It means what I can infer that E induced can be equal to zero. I can write when rotor is not rotating, right? Because EMF induced is directly proportional to omega, and when you close the switch, you can write current, armature current, will be equal to V minus EB by RA. Why? We could have written EB minus V by RA, but here, since rotor is at the stationary point, so EMF is zero, right? So here current should enter the armature. So it should come from the current should be supplied from the terminal, and it should enter the coil. Okay, and that will try to induce the torque in the machine or torque in the coil. Right. So let us find out. This V is given right here 120 volt, and RA is also given 0.3 ohm. So here current will be 120 by zero point 0.3. So it will be approximately 4, 400 amps. Okay, that much armature
Yes,
current
sir.
will, yeah.
Yes, sir. At the starting, the EMF induced will be zero.
Because rotor is at a stationary, right?
Okay.
If rotor is a stationary, your induced EMF will be zero because E is equal to K phi omega.
Yes, sir.
Okay, you know this expression, right? E is equal to K phi omega, torque is equal to K phi IA. These are the very useful, and very often they will be used. Let me write these expressions for you. E is equal to K phi omega. Okay, so in terms of speed in RPM, you can write Z phi n by 60 T by A. I hope you are aware with this expression. Similarly, here if you want to find the value of K, okay, so n, omega is equal to 2 pi n by 60. So n by 60 we can plug in omega by 2 pi. So E is equal to Z pi omega by 2 pi to P by A. So here K will be Z by 2 pi into P by A. Right? So this is the expression of K, and this K will be used in torque expression, where torque is equal to K phi IA. Am I right? Any problem in these expressions?
Sir, please explain one more time this. E is equal to Z phi omega.
E is equal to K phi omega. Okay, since EMF will be induced only when your coil flux linkage will, link to the stator flux. So if it will be rotating at certain speed, then only it will link the flux from the stator or from the field coil. So in that manner, it has to rotate at certain speed. Then only EMF will be induced. So that's why we write EMF. It is directly proportional to a speed and flux linkage.
Okay.
So you haven't gone through the lectures?
No, sir.
Okay, it's okay, no problem. So should I derive it for you if you guys agree, then I can derive it for you.
Yes, sir, please.
Okay. So
Sir, I think in 8 week, this this days are not drive in first week.
okay, okay, no problem. No problem. So see, let me use this figure, right? This is your coil. This one is your coil. Okay. So its current is going into the page and it is rotating, right? It is rotating and your flux is flowing in this manner from north to south. So what is the EMF induced in such cases? V cross B into L. I can write it right.
Yes, sir.
Okay. Now, if these coils are at this position, perpendicular to the, you know, this speed is perpendicular to the magnetic field, then only EMF will be maximum. So I can write EMF is equal to VBL. And V, we know that V will be equal to this R radius, right? V is equal to R radius and omega angular frequency or angular speed. Okay. So I
Okay, sir.
can write EMF is equal to R omega V into L. Okay. So
Yes, sir.
we have arrived here. Now, what is B?
Phi by A.
Phi by A. Okay. And area is equal to, since this is a cylindrical case, so area will be equal to rotor surface area is nothing but 2 pi RL because it is a cylindrical, right? Rotor is a cylinder. You can imagine rotor is a cylinder, right?
Okay, sir.
So it will be 2 pi RL. Now I can plug in here phi by 2 pi RL. And whatever the EMF will be induced, that will depend on the poles. Okay, so if it is, let me simplify it here once. So EMF induced will be equal to 2 RLB omega. Why I am multiplying with the factor 2? Because whatever EMF induced here, E plus, right? And whatever EMF induced here, and if you see at the brush connection, okay, so E A minus EB. So EMF polarity, if you do, force is acting here on the this side, force will be acting here this side. So overall, both forces are adding or helping each other, right? So you can write the EMF induced by this coil and EMF induced by this coil, both will be added, and then overall EMF you will get. So that's why I am multiplying it here. EMF induced in a, you know, combination of coil. In a coil, basically two conductors are there. So for one conductor, it is B omega into R into L from this expression. And I am multiplying it with 2 since there are two conductors. And this expression is valid only under the pole faces. So basically, if you see the EMF induced curve, they will be like, oh, sorry. Okay, so it will be 2 R, sorry, it will be R L B omega, it will be minus R L B omega. So this will look like an AC kind of graph to you. Okay, so this kind of EMF will be generated there, and with the help of commutator and brushes, you convert it, and essentially what will happen, it will be shifted upward. Okay, so it will be like this. Now you can see that there is DC component with some ripple. Okay, so that kind of EMF will be generated, that kind of EMF. And why this kind of behavior is happening, why this kind of graph is there. So let me go back to the figure here when a rotor is rotating. So you can see when the graph is, or when the conductor is under the pole, under the influence of this magnetic field. Okay, then this maximum is coming here. And as you go away from this point, your EMF will drop back to the zero, right? So this looping curve is related to where this graph, this portion is related where conductor is not under the influence of the magnetic field. Okay, so that is why you will lose the induced EMF will not be induced at that certain particular position. So it is, this variation is with T, or you can write it position theta. Okay, so it is dependent on position EMF. It is not a flat DC, not a constant DC. It will have certain ripples in the EMF induced. Okay, that you agree, right? You understand that EMF, whatever is induced, that is not a flat DC. It will have certain ripples, and this ripple will be reduced as you increase the number of poles. Why? Because there will be gap, very less gap in terms of commutation. So this gap, what, how much you will reduce? This is the commutation overlap, right? So as much as you can reduce this, you will get, you know, more more tend to DC component and lesser ripple in the induced EMF. I hope it is clear till this point.
Sir, I have a doubt at earlier equation, sir. Sir, for flux, calculating B, we have written the area pi RL. This pi RL is the
Uh,
surface area of a cylindrical rotor,
yes,
sir.
yes.
Sir, for that cylindrical surface, the net flux is zero, sir. Then B will be zero because the flux entering from N is same flux is going out. Therefore, no net flux is there in the area.
Sorry, I didn't get your problem clearly. Could you please repeat it once more? So this is
Sir,
a cylinder, right? This is a cylinder. So you are saying that flux is flowing, right, here, and this cylinder will be like jointed. Okay, let me joint it for you. Now, like this. Do you agree?
yes, sir.
Uh, so this whole area is what? This length, this length. Let me, this length. Okay, and the radius of the cylinder, this radius, sorry, I think I did mistake. uh, Length is axial, right? This should be r by 2 here, where you are confused.
Sir, in this cylindrical surface, from N side flux is coming, from S side flux is going out.
Out, right, that is correct. Yes, so they are not going out into the air, they are not going out like this, they will come back through this this core, right? You have this iron core. So do not think like North Pole is supplying magnetic field, okay, and whatever traveling through the conductors and they are going out in the air. Why they will not go out into it? You are thinking like that?
Sir, I am saying that, sir, the amount of flux going in and the amount of
Ah,
flux going out are the
ah,
same. Then
are
the
the same.
value of phi would be zero, sir. Then B would be zero, sir.
No, 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 no. So see, there is some misconception here. Let me clarify it for you.
Okay, sir.
Okay, it's fine. Since flux is not a visible component, so it happens. Uh, okay. You have a North Pole, you have a South Pole. North Pole is supplying certain magnetic field, okay,
Okay, sir.
and South Pole will here flux will enter this South Pole. And since outside of this core there is air, right? These all mediums are air, okay, whatever you see. So this flux, which will come enter into the South Pole, that will again travel back to the North Pole through the core. Okay, so they will not just fly away, they will complete a flux loop. There will be certain flux loop like this, like this. You might have seen such kind of flux contour.
Yes, sir.
So I have a I have a software where I can show you such kind of flux path. So since I do not have ready right now, but in the next session, I will try to visualize this flux paths, right? So with the help of a software, and with the help of that, you guys will be easily able to see the how the flux flows, how the armature MMF comes, how the all sort of things happens in the machine. So that is very important to visualize. So I used to show this kind of stuff in my earlier sessions. So I will bring in the next session so that it should not be confusing for you guys, right? So I understand it is confusing because you are not able to see anything. But just for time being, you take it from me that this flux will complete its loop. It will try to, link this conductor, this flux, and it will try to complete its loop just like a transformer. See, in a transformer, we had such kind of finite. So this was producing the flux, right? And if you induce an air gap here, okay, so here it could act as a north and act as a south, right? So here this flux is coming and this flux is entering. Sorry, this flux is entering, leaving the North Pole, and this is entering the South Pole. It doesn't mean that flux is zero. Why? Because in the core there is finite flux. Okay,
Okay, sir.
are you getting the essence of this? What I'm
Yes.
trying to convey? Yeah. So that's my point. So uh, they will not go out of the core. They will try to confine inside the core, and they will make a loop, and that is what we call number of poles. Number of poles is not what you physically assign. You just place two kind of magnets and that will create two poles. That is fine. But two poles is this how many number of flux loops are generating in the machine. That is also called as a number of poles. If
Okay, sir.
this machine is not completing that many loops, then there is no point of placing two poles physically.
Okay, sir.
Okay, so I will show in the next session with the help of simulation, and it will be very, visible, and you can relate to it. So for this time being, you take it that flux will be not zero. In the core, flux should be finite, such that air gap will have certain finite flux, and then only your torque or EMF will be induced or produced. Otherwise, torque will also be zero, EMF will also be zero. And we see, if some company is designing a DC machine, okay, so it is designing certain, width and length of the core. So that is dependent on how much flux is flowing. So you see the saturation level of this silicon steel, it has 1.8 Tesla of limit. Okay. So if they have a certain finite width of core and it has a flux, so it should be near to 1.8 Tesla, otherwise they will lose in terms of utilization. So
Okay, sir.
cores are designed with keeping in mind how much flux density will be there in that core. Okay. So let us go back where we were, right? So,
And sir, why this EMF will shift above the axis?
with the help of commutator and brushes. So see, brushes are the stationary, and whatever EMF. Let me draw. See, they are connected, EA, EB. Okay. So what this is a coil, right? I think you are getting it. This is the coil. This portion is active, and these are the overhang. So there is no point. There will not be any induced EMF in the overhang. So in one coil, its polarity will be like that. Because of this, there are certain number of conductors and flux linking in the part A of the coil, just like in this figure. This CD, in CD coil, there is some EMF will be induced because of flux and speed. And similarly, in AB, there will be certain EMF will be induced, and that will be in this fashion, such that both are get added. Otherwise, if both will be subtracted, then there is no point of connecting the coils. So we are by the nature, by the virtue of magnetic flux. If one coil is rotating in one direction and other coil is rotating in the other direction, as you see in this figure, okay, so both are aiding each other, right? If this is traveling in this direction and this is traveling in this direction, so essentially both are traveling with the same speed in one direction. Are you getting my point? So both EMF will be added, whatever the EMF is induced in this coil and this coil. If you take this dot product or cross product, you will get the polarity such that you will solve in the problems also, so that you will get better clarity. So this is connected to the brushes, and at the brushes we are collecting this both EMF. So EA minus EB will be equal to 2E, whereas is 2RL omega B. Is it fine?
Yes, sir.
Okay. So we were deriving, yeah, where is the derivation went? 2RLB omega. Yeah. So here we were trying to manipulate B in terms of flux. Where is that? Huh. So here B is equal to phi by A. It is equal to phi by 2 pi RL. And if you plug in, you will get, if you plug this expression into this one, B is equal to 2 RL omega into B is equal to phi by 2 pi RL. Okay, so RL and RL will cancel out, and you have Pi omega by 2 pi. Okay, so if you further manipulate, and yeah, here two terms are not connected. One is number of poles and other is parallel path. So if here we have considered total flux, but flux will be generally under the pole. So whatever flux is linked, you can analyze in terms of number of poles. So whatever one pole pairs is generating flux, so hence we always deal with flux per pole, right? So if you further break it, so flux per pole, this is the total flux. So flux per pole will be phi p into p. So this will be the total flux. Here we are using total flux. This is total flux, and total flux is flux per pole into number of poles. So if we further simplify it, it will be phi p into p into omega by 2 pi. Okay. Now again, it will depend on the terms winding. Okay, what what will be the number of parallel paths when it is connected as a lap winding or wave winding. We will go into detail of lap and wave winding, but for time being, you just take it from me that in lap winding, parallel paths are the number of poles in lap winding, and parallel paths are always two in case of wave winding. Have you heard of this term?
Yes, sir.
Okay, so if you have heard, it is fine. You might be understanding that what is the reason behind it. If you do not understand it now, we will clarify it when we will solve the problems based on this topic. Okay, so there are a lot of uh, you know such kind of stuff to realize, right? So this is essentially your EMF induced. So now you are convinced that why EMF is coming like K phi omega. So this is phi, this is omega, and whatever constant is there, that will be known as a K. Okay. Now you got it. Why EMF is directly proportional to K phi omega. It is coming from the your basically motional EMF concept. EMF is equal to VBL. So it is not something very different.
Yes, sir. Sir,
Okay.
in VBL, V is the velocity, right?
Yeah, V is the velocity of the conductor.
Yes, sir.
Yeah. So yeah. So and it is all about EMF induced, and uh, I will try to complete it with torque derivation. Okay. So torque okay. So let me discuss the torque expression for you, just for the sake of completion. How to derive torque? EMF induced. Is my network breaking down? Is my voice breaking?
Yes, sir. No, sir, your voice is not breaking, but there is some another sound is coming due to network issue.
Mm, yeah, I think, but it should not happen. Now is it fine?
Mm.
Yes, sir.
Yes, sir.
Okay, so I think I am audible properly now. Please let me know if my voice will break. Okay.
Okay, sir.
So we have derived EMF induced with the help of our basic concept of motional EMF. How to derive the torque expression? Torque, I told you, it is uh, K phi IA. Okay. I have written, and many times you will also write in future very conveniently. Okay, it will be by hearted to you guys. So how can we write it in terms of K phi IA? How to derive it? It should also come from certain basics, right? Because machines, all the concept of machines comes from basic electromagnetics. So Torque is equal to R cross F, right? And if whatever you know from Lorentz law, what is the expression of F?
BIL.
BIL, correct. So essentially it is IL cross B, right? And again, when your conductor length is perpendicular to the flux direction, you will have the maximum force, right? So, and your conductor is, or conductor current is parallel to the magnetic path or magnetic flux flowing, then your force will be zero. So let us assume at the instance where conductor is, you know, perpendicular to the magnetic flux. So I can write conveniently ILB. And torque, further we know R cross F, so I can write RILB. Okay, and this much amount of torque is induced in one coil. Sorry, one conductor of a coil. You guys understand the difference between coil and conductor, right? So if there is this coil dot and cross, so they will make a coil with the help of number of turns. Okay. So
Yes, sir.
this portion is conductor, and this portion is coil. Okay. So this essentially, whatever the number of turn is there, it will be one coil, and number of conductors can be multiple of integer. So here, uh, in one conductor, the induced torque is RILB. So for a coil, the torque in a coil will be 2IRLB. Okay. Now again, we have to break B or manipulate B in terms of flux. So B is equal to how much we have computed? B is equal to 5 by 2 pi RL, right? So B is equal to 5 by 2 pi RL.
Sir,
So if, go ahead.
if our rotor we want to design in another shape, then this area will change or not?
Uh, Area will change, definitely area will change, but how much area there in a pole, right? That will depend on the area of the pole. So basically, I told you total area 2 pi RL, but essentially we are discussing with the pole per pole. So uh, just like in the expression of induced EMF, what I told you that this phi total is phi p into 4, and phi p will come with the help of 2 pi RL divided by p. So whenever area you will use in the expression with the number of p, right? So whatever area you will use in this expression, in the final expression, to compute this phi p, because in final expression you have phi p, you do not have total flux. So you have k phi omega, phi p omega, and this phi p will be, you are given with magnetic flux density, okay? So into 2 pi RL by P, okay? So how much number of poles? And it will depend on the radius, okay? It will depend on the length of the core, okay? So how much axial length, how much in the z direction, this z direction length, and how much is the radius of the your cylinder or core, so this radius. So it will depend on the dimension of your core. Is that what you are asking?
Yes, sir.
Is it
Sir,
clear
I
or
was
any doubt?
asking that suppose here, sir, suppose here we are using the cylindrical shape core, right?
Mm-hmm.
If we want to design rectangle shape of core, then the area we have to change or not?
Uh, Definitely area will change. If you will design a rectangular, or however, and that is that. may not work because of certain reasons, but yeah, of course, if you change the dimension from cylindrical to rectangular, then your area will change. Yeah.
Okay, sir.
Yeah. So coming back to this torque induced value, okay. So you will get just let me plug in the value of B into torque induced. So 2 I R L B is equal to 5 by 2 pi R L, and 2 R L will be cancelled. Here pi I divided by pi. So here constant is coming to be pi, and this 5p into p you can multiply. So here k 5p into I. So I hope now you are getting from where this torque is directly proportional to flux and current, flux per pole and current, whereas EMF induced directly proportional to flux per pole into speed. Okay, so whenever you see the torque, right, it should directly link to your mind that it is related to flux and current. And whenever you see the EMF, automatically it should be come to your mind that it will be linked to flux and speed. Okay, so I hope it is
Okay.
clear to you.
Yes, sir.
Okay, so I think should we come back to the problem? Yeah. So I was talking that what will happen when the switch will be closed. So initially your coil is not rotating, so induced EMF will be equal to zero, right? And at that time we computed that current is equal to 400 ampere, right? Now we can compute our induced torque as well, because at the time of this instant current is 400 ampere, so there will be some torque. Do you agree? And it is equal to k phi ia. Okay, so
Yes, sir.
let me take certain different places. So k phi ia, and k is nothing but we have found out the value of k here, z by 2 pi into p by a. Okay, so p by a and z by 2 pi didn't come into the picture because we haven't discussed the parallel paths and type of windings, wave winding, lap winding. Okay, so uh, this machine is a two pole, right? I think it is a two pole machine, or anyway, it is shown in the figure that there is only two poles. So if machine is two pole, you do not need to worry whether it is a two pole or four pole, right? So you can write it torque is equal to this term will be we will ignore, okay, because p is 2 and a is also 2, whether it is a lap winding or wave winding, because the minimum value of parallel paths should be equal to 2. Okay, it could not be 1. The minimum value will be equal to 2. So we are ignoring this point. So we can write that z by 2 pi, okay, into phi into ia. Okay, fine. Now to find out the flux, we know here current, we know the number of conductors. Okay, how many number of conductors in this part in this problem? Two number of conductors, right? Because nothing is mentioned, and you can easily see there are two conductors which are making a coil. Okay, so that is why I am telling you here two conductors are there. So because of two conductors, we can plug in z is equal to 2 So the major thing is to find the value of flux per pole. Okay. So how to find out the flux per pole? Flux per pole will we are given with the what are the data we are given with? We are given with the what are the useful data is there to find out the flux density? Oh, sorry, flux linkage. 5 flux per pole.
Sir, we need area.
We need area, right? For area, what other data you could use because area is not given directly.
Sir, 2 pi RL.
2 pi RL. So L is given as 1 meter, R is given as 0.5 meter. So we can use it.
So I think this question demands a qualitative answers and not quantitative.
I got that. I know because I've taken this question, but in the further part, you will require to find out these components. So when you require to compute these parameters there, here you can directly compute it, right? And you can use it straight away in other parts. So that's why I am doing effort right now so that it will be saved later.
Yes, sir, we can do this for simplicity.
Yeah. So we know that when switch will be flowed, current will flow from outside to inside, then it will act as a motor, right? And when EMF induced will surpass the terminal voltage, it will act as a generator. So we were deriving this value of flux per pole, which is equal to B into area. Uh, B is given as 1 Tesla. Area is, we can compute 2 pi RL, okay, divided by P, and here 2 into pi into R was 0.5 into 1 divided by 2. So it will come out to be pi by 2 volt second or Weber, right? Volt second. So flux per pole we have computed. Now coming back to this torque we have 5 by 2 pi into Ia. So pi we have computed pi by 2 into 2 pi into Ia is 400 amps. So this 2 and 2 and this pi will also get cancelled out. So torque is 100 Newton meter, which will be generated, right? So at this instant, uh, if your current is 400 amps, and why it is 400 amps, and why it is so important to compute this starting torque, because you know as your rotor starts rotating, your EMF will increase with speed, right? So here you see this EB. As your EB increases, your IA will reduce. And since your IA
Yes,
will
sir.
reduce, the quantity of torque will reduce. So that is why at a starting, high torque is required. This is very important point, okay? At a start, and even in the characteristics of the machine, you will see at a starting torque requirement is very high. And as you applied this amount of torque, your rotor starts rotating and torque requirement will reduce. So that's very important point I wanted to emphasize. Okay. So this is what will happen. And so first part was this. What happens when the switch is closed? Now I think
Sir,
we are
I
going
got
to. Uh,
Sir, I got torque is equal to 200. Why?
Okay, there might be some factor of two. Either I must have left or you must have left. So let me see.
Sir, K is equal to 1 by pi.
K is equal to 2 by pi. It should be right. K is equal to 2 by pi.
No, sir, 1 by pi.
Okay. Uh, B omega area per pole. See, just let me simplify what will be the value of K in terms of pi or 2 pi. So EMF was 2R omega BL. Okay. In a coil, 2R omega BL. And area per pole is 2 pi RL by 2. So it will be pi RL. Now we can write RL. RL is equal to AP by pi. So EMF we can write 2B omega into AP by pi. And if you further simplify B into AP, sorry, here it should not be omega, it should be pi. So B into AP, okay, into omega into 2 by pi. So it's going to be equal to 2 by pi into BAP will be flux per pole into omega. So it will come out to be 2 by pi. K is equal to 2 by pi. For this particular case, K will be equal to 2 by pi. So let me see what I have used here. If uh, AP, okay, no, here it's going to be 2 by pi. 2 by pi into phi IA, and further if you simplify it, phi t was pi by 2 into IA is 100. So it is coming out to be 100 Newton meter. Sorry, so it will come out to be 100 Newton meter, not 400 Newton meter. Okay, and this should be the highest value, right? So I think if you have any doubt how this 2 by pi came, earlier I did mistake. I wrote instead of 2 by pi, I wrote 1 by 2 pi. So it should be 2 by pi. Any doubt
Sir,
in this?
from the expression of K, sir, from the expression of K, it is also coming 1 by 1 by pi.
From the expression, it is coming 1 by pi. Let me see.
Sir, K is equal to Z by 2 pi P by A.
Okay, so Z is equal to 2,
2.
and this is 2 pi. Let me see. Omega is equal to 2 pi n by 60, and
Sir, 2 to cancel only will remain 1
okay,
by
okay,
pi.
okay, okay. I think here I left one thing. Pi p into p, and p is 2. That is why it should come out to be 2 by pi. Okay, we haven't connected any path, so from my intuition, this 2 by pi seems to be correct. And if I am wrong, we will clarify in the next session. You just verify it after the session. Okay, so whatever is, the essence is we have to understand the concepts. So this numerical error could be there, but you got the whole point, right? What is the concept behind it? Is it fine? Should we move ahead?
Okay, sir.
Okay. So that was the first part. And torque, I will write it the value of torque 100 Newton meter. If you guys are getting some different, um, there might be error in the calculation or derivation. But essentially, this derivation was to conclude that EMF is directly proportional to flux and the speed. And until we are well versed with windings, type of windings, it is very difficult to plug in all the values of panel paths and the number of conductors and poles. So that is why these errors are coming. But anyway, we will solve one or two more problem in some next session, so we will be clear with it. So in part B, it is asking what is the machine's maximum starting current and what is its steady state angular velocity at no load.
So starting current will be 400 amperes.
A starting current will be 400 ampere, which we just calculated, right? So it is correct. The starting current is 400 ampere. And what will be its steady state angular velocity at no load? So this is a bit
No
tricky for
load.
you. At no load.
Sir, I think 0.
Zero. Why you are saying zero?
Because sir, at no load, there would not be flow any current. So torque will
Uh,
not produce, I think.
okay, you
Torque
are
will not
correct there.
produce.
You are correct at this point that at no load, torque will not be produced. That is correct. But why there will not be any speed or any velocity of the coil? Because
Sir,
see,
without
go ahead. Yeah.
without torque, motor how can rotate?
Okay, so without torque motor, how can it rotate? That is fine, but maybe motor was rotating earlier and now current is zero. So what will happen? At a steady state, it is asking. Mind it, it is not at it is not at when rotor is a stop. Rotor is not a stop. It is at the steady state condition. At a steady state condition means your rotor was rotating at certain speed. Essentially, it could
Constant
be
velocity, sir.
rated constant velocity. Yeah, that is right. So it was not at a stationary condition.
Okay.
Okay.
But sir, at the time tends to infinity, ultimately, I think it should be
See, okay.
log.
Let me
Log.
further clarify it for you. If your motor is rotating at a steady state at a speed of omega, right? So, and at a steady state, let us assume it was at rated load. Okay, constant speed and rated load. Okay. Now you suddenly remove the load. Okay. Now what is happening? What you are doing? Load is removed. You just have to let me know whether omega will reduce or increase.
Sir, I think it will
Sir,
increase, sir.
Okay. Neeraj's answer is increase. Deepak, you tell me what will it be. And others, whoever are there, you can also let me know what will happen. Okay, so what will happen, Deepak, Preeti?
Sir, we have removed the load but not the supply.
We have removed the load but not the supply. That is correct. Yeah, here you are correct.
So, sir, speed will increase, omega will increase, I think.
Omega will increase. Yeah, that's what I wanted to hear. So yeah, omega will increase. As you remove the load, your speed will be increased. Okay. So, and why it is increasing? Let me derive or let me compute what will happen to the this angular speed. Okay. So whenever a speed in the question it is asking, what you should relate it to?
Current.
No, no. Uh, Current is related to torque, right? You remember, I told whenever torque will come in picture, you relate it with current, and whenever the speed will come in picture, you have to relate it with
Philip,
EMF.
EMF. EMF is the strong linking thing to the speed. Whenever the speed will come in the picture, you have to link it with induced EMF. Okay,
okay.
so induced EMF. So what will be the value of induced EMF here? Just I will let you read the problem. What will be the value of induced EMF in this problem at no load? You see this circuit, okay, carefully. What will happen to the induced EMF? This induced EMF
Sir, at the starting it will be zero, then it will increase, sir.
at a starting, but we are talking at a steady state, no load
Yes,
condition.
sir.
So what will be the value of induced EMF? At a steady state, this switch will be closed, right?
Yes, sir.
Now you tell me.
It will be LV. B cross LV.
No, EMF induced. Now we are shifting into circuit parameters. We are not anymore in magnetic domain. Here, as you leave this portion from right to left, here only KVL you have to apply, and current is zero at no load. Current is zero at no load, right? So E induced will be equal to VB.
VB.
VB, yeah. So this is the equivalent circuit. Let me draw it for you of a DC machine. You have certain supply, for particularly for DC motor. Okay, you have a armature resistance, and this there is this armature coil. Okay, which is rotating at certain speed, which will induce certain EMF. Okay, and this is RA. Okay, whatever, if this if this omega is equal to zero, okay, then EMF is zero. That I agree. But if omega has certain speed, then you can compute this EMF with if certain current is coming either coming from the supply or if it is rotating at certain larger speed such that E is greater than zero. Sorry, E is greater than V, then it is working in generating mode. And when E is less than V, it is working in motoring mode. Why? Because what happens in generator? It supplies to the load, right? It supplies from the generator, the current is coming out of the generator. So when it will work as a generator, current will come to the terminal. And when it will work as a motor, so motor, how does it work? We give supply to the motor and then it rotates your fan and whatever rotating machine is connected, right? So
Yes, sir.
this is the case of motor and this is the case of generator. So
Sir,
that is why.
how can we? how can we say that current is coming out or coming in into the generator or motor?
You have to just identify what is larger, which parameter is higher, VB or E, supply voltage or back EMF. If you rotate your
Okay.
rotor at high speed such that it surpasses the value of VB, then you are working in generating mode, and that is what happens in
Okay.
uh, regenerative braking. You might have heard in electric vehicles they are using regenerative braking to charge the battery. How does it happen?
Yes, sir.
It happens in such way that you break it and you have certain you know EMF will be larger than your terminal or DC link battery, and your current is going into the battery rather than it is coming out of the battery. So it is charging your battery. So that, and in power electronics also you will study in rectifier topics. You will study that battery charging circuit is connected to a thyristor bridge, right? So there also it happens. So that is how you decide, right? In which mode it is
Yes, sir.
working. Okay.
Okay, sir.
So yeah.
Just we have
So
to calculate this EG.
huh.
You know, sir?
Yes. Yes. So
Okay, sir.
induced. We were talking about, or we need to compute angular velocity or the speed of the rotor that is linked to induced EMF, and induced EMF is equal to 2 by pi phi omega. Okay. And it will come out to be induced EMF is equal to VB, and VB is given in the problem. It is 120 volt. Okay, it is given in the problem 120 volt. So 2 by pi omega is equal to 120. Okay. Here omega will be equal to 120 into pi by 2 into phi. Okay. And phi we know that we can compute is equal to B into A, and B was given area per pole is equal to pi RL. Okay. So this pi and this pi will be cancelled. So it will be 60 divided by RL. R was 0.5 m meter and L was 1 meter. So it will be, sorry, how does it 60? dB was 120, right? 120 divided by 2. Okay, so B was
Sir,
how
here we
much?
will take.
No, no, no. Okay, so B I would 1 Tesla. It is, sorry, V is 0.25 Tesla. Okay, L is 1 meter, R is 0.5 meter. Okay, and VB is 120 volts. So these are the parameters we need. So this
Sir, here phi
by
is the
the
flux per pore or total pore.
flux per pole, right? And here flux per pole is the total pole, right? Because in one pole pair, whatever flux is, there are two poles total in this circuit or in total in this motor. So you can say that total flux is equal to that, right? So it is 120 divided by 2, 2 into 0.25 into R into L. So it will come out to be 480 radian per second. This is the angular velocity at which rotor will rotate at no load. Okay. What will happen? You understood till this point, right? Any doubt? You got cleared why I am using flux per pole is equal to total flux?
No, sir.
Okay, no. So see, this area, whatever flux is flowing, total two poles are there in this armature, okay, or field. There two poles of field is present. If you increase the number of poles, as you increase the number of poles, your flux will be divided in four sections. Right, one loop will be like this, one loop like this. Okay, so here flux per pole will be reduced, but total flux will be same. You agree? Because
Yes, sir.
core is restricted to cater only limited amount of flux. And if you are increasing the number of poles, you will have to increase or you have to decrease the flux per pole. So that is the thing here. And here I for two poles, whatever for two poles, let me write for two poles, whatever the flux per pole is coming out from the north pole, it's going to the south. So here I think I did divided by two. Yeah. So area I did divided by two. In area, I included that factor of two division. Okay. But as you go ahead with higher number of poles, you have to take care of this. And we will solve the problem for higher number of poles as well. So it will be clear. But if you understood that if you increase the number of poles, you are just distributing the flux for different sections. And why higher number of poles are required? Because as you increase the number of poles, your cross section of core will also reduce. That we will talk in some different lecture because that will be a bit out of context. Okay. So I hope you understood till this point. Any
Okay,
doubt in
sir.
this?
And sir,
Hmm.
sir, I did not understood this. Why this VV is equal to EMF induced?
That I will tell you. See, uh, okay. So as you close this switch, okay, from the KVL, what do you see EMF induced is? EMF induced is VB minus IAR, right? You agree till this point?
Okay, sir.
From this KVL, from the KVL, if you apply in this loop, EMF induced will be VB minus IR, right? This current, if this current will flow, let us assume certain load is supplied from the this terminal, then it will have EMF induced value will be EMF induced will be VB minus IR. And this is also equal to K phi omega, right? Now what will happen as you increase this load? If you are increasing the load, either initially it was at no load, now you are increasing the load. What is happening to the induced EMF? Just from this expression, okay, if you are increasing the load current IA or armature current, okay, what will happen to EMF induced? We just computed at no load how much EMF induced? 120 volt, right? At no load, we computed 120 volt. Okay, so let us assume when I not assume IA when IA was zero, EMF was 120 volt. Now R is given in this one, 0.3 ohm. Okay, so zero point 0.3 ohm into IA. Let us suppose IA I am increasing from 0 to 5 amps or 10 amps. Okay, so 10 amps and this is 0.3 ohm RA. Now IARA is 3 volt. You agree? Any doubt till this point?
No, sir.
No. Great. So now what will be the value of EMF induced? 120 minus 3. It will be 117 volt. Fine.
Okay.
So its impact on velocity, how it will affect the velocity or the speed of the rotor. As your EMF induced got reduction, right? So a speed also has to follow that. So now, since you increased your current from 0 to 10 amps only, your speed will reduce whatever 480 radian per second was earlier, right? So let us 120 volt was corresponding to 480 radian per second. Now your 117 volt, what will be the speed? The speed will be equal to 480 into 117 divided by 120. How much it will come? Please compute it for me. How much it will come? 480 into 117 divided by 120.
Sir, 264, I think.
264. 264. No.
468.
468. Yeah. 468 radian per second. Are you able to see the instant effect of this loading? As you increase just 10 amps in the circuit from 0 to 10, your speed reduced from 480 radian per second to 468 radian per second. So you are just providing load and your speed is getting reduced. So that is the essentially load characteristics of the motor, of this DC motor or DC generator. Is it crystal clear to you? Any doubt in this? And if you further increase the current, your speed will further reduce, your EMF induced will further reduce. Fine.
Okay, sir.
How speed, current, torque, EMF, how they are interrelated. So that is very important to relate all the parameters in your mind. Okay, you just think, okay, you have a cup of tea and think that how they are linked with each other. You will be able to conclude this in your own mind. And once it will be fixed in your mind, it will be fixed forever. Okay, so let us move ahead with the next part. Okay, suppose a load is attached to the loop, okay, and the resultant load torque is 10 Newton meter. What would be the new steady state speed, right? See, this is essentially asking the same thing what we just discussed. Okay, so we were anticipating that kind of question or that kind of problem will arise. So here it is. So we have just attached a load of 10 Newton meter. This load will draw certain current. Okay, so that is why it is asking what would the new steady state speed be and how much power is supplied to the shaft of the machine. Okay, and how much power is being supplied by the battery. And finally, you have to conclude, is this machine a motor or a generator? Yeah, it has 4 parts. It's pretty long, but it's also very interesting, you know. Yeah. So what should I do? How should I proceed? The first step, the first step should be as soon as my eyes goes on to load torque 10 Newton meter, the first thing my pen should do is to calculate the current, how much current it will draw at that torque. Am I am I right?
Yes,
Yes, sir.
sir.
Yeah, so I will, first thing I will do is to find out the current. And the relationship between torque and current is K phi Ia, right? K phi Ia. And here we have taken K as 2 pi pi. So do 2 by pi into phi into Ia. Okay. So we can write torque is 10 Newton meter is equal to 2 by pi, and phi is nothing but the same thing, uh, B into A into IA. Okay. So first let me find out the phi. We have already found out. So IA will come out to be 10 divided by uh, 2 by pi into 2 pi RL by 2 into B, which was 0.25 Tesla. Okay, so it will be equal to 10 divided by pi. Pi will be cancelled, 2 will be cancelled, then by 0.25 into 1 into 0.5 into 2. So it will come out to be uh, 40 amps. Okay, so at 10 Newton meter, either you are drawing or supplying, okay, to the terminal 40 amps. Okay, I hope it is clear. Now coming back again to the question, the next thing is, it is asking what would the new steady state speed be? What can you conclude from this second statement? This statement, what would the new steady state speed be?
The speed will reduce, sir,
Speed will
and
reduce. Okay. Yeah, go ahead.
will reduce to some value and stay there.
Stay there. That is fine. That is absolutely correct. But what will that value be?
Sir, we can compute through the EMF induced equation.
Exactly. As soon as you saw that a speed term, you have to compute the EMF induced. Okay,
Because
so
sir, EMF will reduce.
EMF will be reduced, and EMF we know, since you have computed the current as 40 amps, so EMF will be 120
AB minus
minus 40 into
40.
RA is 0.3. Okay, so it will be equal to 14, 12, 108, 108 volt, right? So earlier EMF, we have to find out the two expressions or two equations. When the speed was 480 radian per second, EMF was 120 volt. Okay. Now a speed we don't know. We know that EMF is 108 volt. We know that E1 by E2 is equal to omega 1 by omega 2 into phi 1 by phi 2. But since the flux is constant, because flux density is constant, so we can ignore this phi 1 by phi 2. Both are same. So essentially it is equal to omega 1 by omega 2. Now we have to find out this omega 2. Okay. So omega 2 will be equal to E1 by E2 into, sorry, omega 2 will be equal to E2 by E1 into omega 1. So E2 is 108, E1 is 120, omega 1 is 480 rads per second. Now please calculate it for me. What will be the value of speed? And that will be your answer.
Sir, 432.
432 radian per second. So now you must be able to observe what happened. As Neeraj earlier mentioned that speed will reduce and it will be constant at that speed. in the steady state. And that is the speed when 10 Newton meter of torque your load desires and you have to supply, then your speed will be 432 rad per second. Is it fine? Any doubt?
Yes, sir.
Yeah. So yeah, so coming back to the next part of this part C, how much power is supplied to the shaft of the machine? How to calculate? You know that relationship between power and shaft torque.
So T multiplied by omega, sir. Torque
T
multiplied by omega.
exactly, absolutely. So that power is equal to torque into omega. So let me write it. Omega we have computed. So power is equal to torque into omega. Torque was 10 Newton meters. Omega is 432 rad per second. So how much it will come out to be 4320 watt. So that is your shaft power. Okay, remember, it is your shaft power. It is not your input power. Neither it is an electromagnetic power. What is electromagnetic power? EB into IA, which is at the armature. So it is the shaft power is, let me draw it for you. Whatever you give to the input, okay, there will be some power developed with some copper losses and all, core losses, and this developed torque will have certain mechanical loss, and then your shaft power will. So P shaft is equal to P developed minus mechanical loss. Okay, or you can write P input minus all the losses. Okay, so coming back to the next part, it is asking how much power is being supplied by the battery. So now it is asked that input power. How much power is being supplied by the battery? How to
Sir,
calculate?
4.3 kilowatt.
4.3 kilowatt power will be supplied from the battery. You are saying
Yes, sir.
you are absolutely wrong.
Sir, the current flowing is 40 amperes, no, sir?
Current flowing is 40 ampere and battery supply is 120
120
volt.
volt.
So
Then the power
that's what
supply
you
will
have.
be 4800
Yes,
watt.
correct. That is exactly correct answer. So power input is V into I, V battery into IA, and 120 volt into 40 ampere. So it will be 4800 watt. Did you get it, Deepak?
Sir,
Ah,
sir, VB is 108 volt now.
no, where? Let me show you. Where is it?
Okay,
It is
okay,
120
okay.
volt. Ah,
Okay, sir. Okay.
that's why you did mistake.
Yes, sir.
EMF, this is EMF induced. It is not VB. You understand the difference between EMF induced and supply voltage. Supply voltage will not change, but
Yes, sir. Yes,
EMF
sir.
induced will is dynamic. Yeah, yeah.
Yes, sir.
Now you have to say this machine is operating in which mode, motoring mode or generating mode?
Motoring.
Motoring mode.
Motoring.
Why?
Sir, so the current, applying the passive sign convention, sir, we can see
Uh,
that current is flowing out of the positive terminal of the supply voltage. Therefore, it is
mhm.
supplying power. To,
Right. Yeah. So yes, your EMF induced is less than battery voltage. That is another indication. Okay.
Yes, sir.
Your speed is reducing and at no load. Okay. At no load, both will be equal. And as you start giving very small load, incremental load, okay, and you observe that whatever the direction of current you are following, that is coming according to the question or not. So in that manner, you will be able to identify. So here in this problem, you can see that whatever you have taken the convention E is equal to V minus IRA. So, and that is following exactly what is happening. So it will work as a motoring mode. And your electrical power of 4,800 watt, 4.8 kilowatt is converting into mechanical power of how much? 4320 watt, right? So if you find out the efficiency of this motor, how much efficiency of this motor, it is 4320 divided by 4800 into
So
100%.
90%.
It is 90% efficiency, which is very good for this power rating actually. Practically, you won't get that much of efficiency if you design it, but yeah, it is very good number.
Sir, it is good.
Okay, yeah, it is very good at this power rating of below 5 kilowatt. It is very good number. You won't get it practically. For this kind
Okay.
of power efficiency, you will require very strong magnetic field or very strong permanent magnet.
Okay, sir.
Your
And
field
sir, at
winding,
no load.
at no load, yeah.
And sir, at no load, what will be the shaft power? Zero.
No, no,
No.
at no load, you will have this power. Uh, there will be certain rotational losses, right? You have mechanical loss at no load.
Only.
You have core loss at no load. So without current, copper loss you eliminate. Okay, no power will be developed because power developed is equal to EB into IA. So you will left with only losses, and losses will not come from the sky. It will have to come from supply, right? To rotate the machine, it will incur certain losses, and that will have to cater from the supply, right? It will not be a magic. Yeah,
Yes.
yeah. So should we move ahead to the next part?
Hmm.
Yeah. So part D. Suppose the machine is again unloaded and a torque of 7.5 Newton meter is applied to the shaft in the direction of rotation. What is the new steady state speed? And is this machine now a motor or a generator? Okay. So with this one problem, you will be very well versed with this kind of relationship. And believe me, it will take, if you learn it, it took 1 to 2 months for me to understand. After solving a lot of problems, then you will be well versed. But that is the beauty of such kind of long problems. You will able you just solve this problem 1 or 2 more times. You will be very well versed with this concept. So that's why when torque of 7.5 Newton meter is applied to the shaft, we have to, again, we just saw the torque parameter. What we have to do, again, we have to do the same thing. We have to compute the current, right? Now it might be there in your subconscious as well. If you see the torque, now from the next time, you will straight away calculate the current. So I will do that. Okay. So when torque was 10 Newton meter, current was 40 ampere. Now the torque is 10.5 Newton meter, current I don't know. I know T1 by T2 is equal to phi 1 into I1 by phi 2 into IA2. Fine. Let's find this expression, this ratio. This ratio is very useful. You have to apply everywhere. If you know one case, you have to derive for the other case. You have to apply this ratio. Okay.
Okay,
Okay.
sir.
Okay. So now I want, since flux is constant, we always assume, since it is mentioned at the beginning of the problem, flux density is equal to 0.25 Tesla. So we will always have to consider, and in most of the cases, flux will be constant. Wherever it will not be constant, you will be mentioned as either that flux is weakened in this case or flux is reduced. You will be given, right? So I will try to compute IA2, which will be equal to IA1 into T, T2 by T1. And IA1 was 40, T2 is 30, T1 is 10. So for IA2 will be 120 amps. 120 amps. Earlier it was 40 amps.
T2 is
Okay,
sir,
okay.
T2 is 7.5.
Yeah, that's why. See, if you know the practical concepts or applications,
30.
you will also be able to figure out where you are committing a mistake. So this is 3, this is 4, 10, 30, 30 amps. Okay, so when 7.5 Newton meter is applied, at 30 amps of current you are supplying to the load. Okay, so we are done with the current. Now
Sir, it is extra current we are injecting to the supply from the supply.
it is extra current. I wouldn't say that. Why? Because earlier it was where it did it go? Huh. Earlier it was 40 ampere, now 30 ampere. Why? Because a speed has to increase or reduce from 10 Newton meter to
Reduce.
you are coming back to uh, no, at 10 Newton meter you are reducing the torque. When does your torque get reduced? As you release the load, as you reduce the load, and load is reduced, so your speed should be increased.
Yes, sir. But sir, in problem they are saying we are
Hmm.
applying the 7.5 Newton
Meter in the
torque.
direction of rotation.
Yes, sir. Means we are adding more torque.
Yes, yes. So it means the speed will increase. Torque, what
Yes,
will
sir.
torque do? It will accelerate the rotor. Do not leave basic. Basic is always there. As you are applying torque to the shaft, rotor will accelerate.
Yes, sir.
And as the speed increases, what will happen?
As the speed increases, current
Uh,
will
no, no.
reduce.
When I am mentioning in the first sentence, when the speed is increased, then in the second sentence, it should be EMF induced will be whatever.
Increase, sir.
EMF induced will be increased. Yeah.
Yes.
So in such cases, you are applying torque to the rotor with current of 30 amps. So it may exceed the battery voltage or supply voltage, and it may enter into the generative mode. Okay, so let us compute what will happen. Now you are applying to the torque to the shaft, and it is applying external force, external acceleration to the rotor, and EMF induced will surpass the supply voltage. So I can write EMF induced will be V plus IARA, because this is not in opposite direction. So that's why this polarity is changing. It is in the direction of rotation. So that is why it is plus. And here 120 plus 30 into 2.2. So 129 volt. Okay, so 129 volt is there. And what will happen to speed? Now it's very interesting. What will happen to speed? We know the constant, right? EMF is equal to 2 by pi omega. Okay. And EMF is 129. So a speed we can calculate here. Or from ratio also you can calculate. That will be very easy. So E2 by E1 is equal to omega 2 by omega 1. And we have to find out the omega 2. So omega 2 will be omega 1 into E2 by E1. So take any case, it is better to take no load case. That will be straightforward. So 480 radians per second was at no load, and now E2 is 129, and at that time E1 was 120. So calculate it, and you will get the value of this speed.
Sir, 516.
516 radians per second. So it is even higher than the no load speed. Why? Because you are adding external torque. Even at the load of 7.5 Newton meter, mind it. Even not at no load, at the load of 7.5 Newton meter, you are getting higher speed. So how will you get higher speed? So torque and the speed is also interrelated. Not only a speed and your induced EMF, torque and the speed is also interrelated, but it is indirectly related, not very direct. You have to come from current to torque to induced EMF to speed. So these are kind of patterns you have to follow to solve such kind of problems. Any doubt in this part?
Sir, torque and speed, how they relate?
Yes, yes. So if till now you are not able to figure it out, let me clear it for you once more. Okay. So here, coming to this expression again, I hope you are able to see this expression.
Yes, sir.
As you are increasing the torque, okay, you are increasing the torque either in the opposite direction or in the same direction. If, let me take a fresh case. You have applied torque in the direction of motor, in direction of a speed, let us say, it will be convenient. Now, what will happen? This torque is increased, it means your current is increased. Okay. Now this current is increased, EMF induced will be V plus IARA. Torque to current. We are very confident that we can arrive to the current as soon as we see the torque. Now we are done with current. Now what we'll have to do? We will have to evaluate the induced EMF, and it is V plus IARA, and IA is increased such that E is also increasing. And when E is increasing, induced EMF increasing, what will it lead to? We can directly write the speed is increasing. Right. So this is what happening when the torque is provided in the direction of speed. Now, other case, when torque is increased in motoring mode, so in opposite to the speed. Now what will happen? Torque increase, current increase. Okay. EMF is equal to V minus IARA. Now, since we have increased the current, EMF induced will reduce. And when EMF induced is reduced, it will lead to a speed to reduce. Now, are you able to relate all the cases?
Okay, sir. Sir, this positive sign will come in the case of generator and
In the case of
negative
generator,
in
yes.
the case of.
Yes, yes.
Okay. Okay, sir.
And it is not only in the case of generator, also in the direction of a speed. If torque is applied in the direction of speed, if let us say you your torque is not applied in that direction, then generally torque is applied in the direction of speed in the case of generating mode. Okay, that is why in the question it was asked. Otherwise, it would have been a straightforward that in the question just mentioned that torque is applied in the direction of speed. You could have directly concluded that it is acting as a generator, but that is not case. So it is not very generic. It is common, but it is not general.
Okay.
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 So now coming back to the final part. Okay. This is very interesting. Now it is not whatever you have discussed. We have discussed. Okay. Suppose the machine is running unloaded. Okay. What would the final steady state speed of the rotor be if the flux density was reduced to zero point 0.2 Tesla? Now flux density is manipulated here.
True.
So how will you proceed for this part? You have to let me know.
Unloaded. Sir, just I think here our flex have changed.
Uh,
So
flux is changed.
what would be the
Sir,
flex has changed? So
when
our EMF induced will also change.
EMF induced will also be changed. And since we are dealing in terms of speed, we have to relate it with EMF induced. Right. So now
Yes, sir.
our ratio of E1 by E2 will not be any more omega 1 by omega 2. It will have also
Yes,
phi
sir.
1 by phi 2.
Phi
Right.
2, obviously.
Uh, so do not ignore this. Always make sure your flux is constant. Then only you eliminate phi 1 and phi 2. Okay.
Yes, sir.
Now phi is also directly proportional to B1 and B2. And since we are given in terms of B, so it is better to write E1 by E2 is equal to omega 1 into B1 by omega 2 into B2. Okay. Now we know E1, we know omega 1, we know B1. Now in this problem, it is asking that if machine is running unloaded only, okay, and flux density is reduced. So what do you mean by unloaded? So if it is saying that it is unloaded, it means we have to compute according to that. So since this E1 and E2 both will be same at unloaded condition, now
Hmm.
if you further manipulate this expression, omega 1 B1 is equal to omega 2 B2. How come I wrote this expression very conveniently? Because at no load
Yes,
E1
sir.
and E2 will be equal to 0, right? Now omega 2 is equal to omega 1 into B1 by B2, and omega 1 was 480, B1 was 0.25, B1 is 0.2.
Sir,
So, huh,
sir, at no load E1 and E2 should not zero. I think they will equal to each other.
huh, who told 0? They will be equal and equal to 120 volt.
Yes, sir. Yes, sir. I think
Huh.
I have listened that you say they zero.
Okay, okay, no problem. So,
I mistake.
no worry. So, how much value this will lead to?
Okay. Sir, 600.
600 radian per second. 600 radian per second. Any doubt in this point?
And
No, sir.
No. But I would like to have an answer. Okay. First, I would like to have an observation from you guys. What did you observe from this part, specifically, last part?
When the flux density decreases, the no load speed increases.
Yes. Basically, the philosophy to increase the speed, okay, you have to reduce the flux. Why? Because if the voltage is constant, see, this is a very heavy statement. If you have to increase the speed with constant voltage, okay, then you have to reduce the flux density. Why I am saying this? If you would have kept flux density constant, and if you increase the speed, now your EMF will increase further, and it will lead to voltage. You will have to provide additional supply. But now, since you increase the speed and you reduce the flux density, you are maintaining constant induced EMF. So essentially, you are increasing omega and reducing B. It means you are keeping EMF constant. It means V will also be constant, more or less. Now,
yes, sir.
as if you have kept B constant, okay, B is equal to constant, and you are increasing the speed, what you are essentially doing, you are doing EMF increment, and it will lead to V
Increasing.
increment. And that is not very
Yes.
desirable case. Okay, so in that is why every time, and where do we need such kind of application? Where do we need such kind of operation? In any practical example, in practical world,
So
it is
regenerative
applied at
braking.
not exactly regenerative braking, but you are very close there. I am asking
Sir, ceiling fan.
application. Ceiling fan, no, again, because here you don't go beyond
Answer
a certain
regulator.
speed.
Answer by
Regulate,
using regulator. We
uh, you reduce the frequency in VLDC fans. You reduce the frequency, and that is why your speed reduces. But here we are talking, we are increasing the frequency essentially. Since we are increasing the speed, we are increasing the frequency. But we have to maintain, because once you have provided a battery of certain capacity, you will have to maintain it. You cannot surpass that battery.
mm,
And you are reducing this flux, right? You are reducing this flux to increase the speed range. So this is called as field weakening operation. Because you are field weakening and
field
you are
beginning.
increasing it. Uh, and now you can guess where it is applied. Very, very, very popular and emerging thing in India also. Electric vehicle.
Ma'am, yes, sir.
Electric vehicle, haven't you heard it?
Yeah, but sir, how can we reduce
So do
the
the electric
field
vehicles
without
use DC
any
machines or induction machines, sir?
You can use DC machine. There is no problem. You can use, and it is very
BLDC?
convenient. If you use, no, no, we are talking here only DC machine. And if you use DC machine, you will have an advantage. What advantage there? You do not need any inverter. That is in itself a huge thing, huge capital cost. But why don't we use? That is the question.
Sir, why don't we use what, sir?
Why don't we use DC machine in electric vehicles? We use in traction application, locomotives. We still use DC machine there. But why don't we use in electric vehicles DC machines? Or it is not very popular, not very much used.
It requires maintenance, sir. Regular changing of
Exactly,
brush.
exactly. That is the reason. It requires the brushes maintenance, commutators maintenance. It that and you don't want to your vehicle get repaired daily, right? Or even frequently once in a month. So and you do not have access to motor internal brushes and commutation every time. It is not very convenient, and sparking in the brushes is another issue. So that is why brushless came into picture, right? So it is very interesting. And how did we achieve brushless? Because here also with commutation and brushes, right? We are converting AC to DC,
Yes, sir.
and with we are doing the same thing with the help of our converters, power electronic switches.
Okay, sir.
So we are supplying similar type of current, similar type of EMF, okay, and
Yes.
just with the help of switches, without any help of brushes and commutators.
Okay, sir.
But what will be the impact? That is an important point to note and take away from this lecture. What will be the impact if you are doing field weakening? You are reducing the flux, you have increased the speed to maintain the voltage, okay. But what are you losing on?
Sir, I think torque.
Torque, yes. If torque is also is equal to, let me write it, torque is equal to K phi Ia. And since you have reduced flux and current is rated, so torque is reduced. Okay. I hope
Okay, sir.
it is understood. But is there is it fine for EV application or not?
No,
Do it
sir.
does it affect the application or operation of EV if we are losing on torque?
Yes, sir. It will affect, sir.
It will affect. Okay,
Yes, sir.
we will see here.
So there is will be some weight of the vehicle and the passengers.
Yes, yes, you are correct. You are correct. This is the torque requirement of the electric vehicle application. Okay, so as you are entering, as you are going at high speed, okay, at your let's say you are going, your rated speed is 1000 RPM, and you have reached to 2000 RPM. Okay,
Okay.
so now at 2000 RPM, do you require that much of acceleration? What you had required at 1000 RPM, what you would have required at 0 RPM? When you are already moving at 60 miles per hour or 80 kilometers per hour, you do require that much of acceleration, what you would have required at 0 kilometers per hour?
No, sir. I think will have we'll need to maintain a steady speed of 60.
Yes, so no, even at 80, at 2000 RPM or 80 kmph, you need very small torque, and that it is already providing. You don't need higher than this torque. That this is the low torque characteristics of traction application. As you go at higher speed, you don't need high torque. Your torque requirement reduces, and that is fine. And that is what field weakening does.
Okay, sir.
I hope you are getting my point, what I am trying to convey. So it is fine for electric vehicle application, but it is not fine for fan type of application, or it is not fine for pump application or any other application. So that is why you see that constant power speed region, or you might, if you see any data sheet of any electric vehicle of Tata or anything, they will always mention that rated speed is this, maximum speed is 2 times, 3 times of this. They are achieving that with the help of field weakening.
Okay, sir.
Okay.
So all these new electric vehicles, the small auto run on battery, they use DC motors.
They use BLDC motors, brushless DC motors.
Okay, sir.
Okay.
And
They are providing DC current, but with the help of power electronics converters.
okay, sir.
So
And the
basically,
cars, sir.
cars they are having PMSM, sinusoidal AC motors. They are having AC motor, but it's not that you cannot use DC motor there. It is just that AC motors are very much advantageous in such kind of application. Okay, so there are certain things. If you are providing, see, to provide DC machine,
Hello,
you need. Hello, am I
sir.
audible?
Sir, I have a one doubt.
Go ahead, please.
Okay, that is okay. That in electrical vehicle we can we can reduce the magnetic field and the torque will reduce, and that is fine. But sir, how can we reduce the magnetic field?
So how can we reduce the magnetic field? That is very good question. So field is coming from two things, right? Either from you have provided certain coil on the stator side in DC machine. You have provided certain coil in this is the magnetic field. Either it is a permanent magnet or a magnetic field generated by the coil. So coil has certain MMF NI, and that is producing field flux.
Mm-hmm.
Are you getting it? Okay. So now you want to reduce the
Yes,
flux.
sir.
So essentially, what you do, you do the zero current of field current or near to zero. So no flux will be generated
Okay.
from the field coils. Okay. That is what about field coils. I hope you understood, right? Ni is the
Yes, sir.
MMF
Yes, sir.
that is generating flux, and you reduce it, and your flux will be reduced. Now,
And
for the permanent magnet, how will you reduce this field?
not possible.
It is possible. Otherwise, how would people be operating so many cars, trucks, railways with permanent magnet motors? Nowadays, everywhere permanent magnet motors are there. In brushless DC machine, also permanent magnet motors are there.
Sir, we'll energize a coil that will produce a field opposite to these
Exactly,
poles.
exactly. That is the principle. We demagnetize the permanent magnet. We provide armature current such a way that it opposes the field MMF. Right? You might have studied, or you will study in AC machine, that demagnetization component of armature MMF, magnetization component of armature MMF. So demagnetization component will demagnetize and it will reduce the flux in that region. Did you get it, Deepak?
Yes, sir.
Now coming back to the nearest question that what was your question? Okay, so we are achieving here BLDC operation. We are giving a square wave of current. Okay, wherever wherever this kind of EMF is there, right? Now, what is the problem with the square wave current?
Please repeat, sir. What did you ask?
See, you understand this part, this graph,
There is a square wave and
the square wave current and this kind of EMF I have shown you earlier that it is induced from the coils. Let
okay,
me
sir.
let me let me. mm, Okay, so this EMF you recognize, right?
Okay, sir.
This EMF from DC machine you recognize. Now, to produce torque, what you have to do, you have to just provide a current pulse here wherever EMF is maximum, such that E and IA will generate the power or torque, right?
Okay, sir.
So to giving such kind of current pulses, you will require certain power electrons converters.
Okay, sir.
Yes, sir.
Okay. Now, if such current exists in the circuit, what is the problem with such current?
Abrupt change in current.
Uh, that I would not say because that is the purpose of power electrons converter. So if you might you might not be knowing this, as you use a square wave currents in power electronics also you will study it will have higher harmonics.
Okay, sir.
Harmonics problem. And what harmonics does? Harmonics induces your losses very significantly
Okay,
because
sir.
harmonics in current and magnetic flux and EMF even it will lead to you losses and
Yes, sir.
immense losses. And as you go at higher power, you will not be able to maintain high efficiency. And here
Okay,
you
sir.
lose. compared to AC machines where you have sinusoidal current, so zero harmonics in current. But whatever some harmonics will still be there in AC machines because of your winding MMF or special harmonics. But you are reducing from the supply side, so that's what where you gain, and that's why we use PMSM for high-end high vehicle applications, high electric vehicle application, premium electric vehicle applications. We use PMSM, and for e-rickshaw, three-wheelers, two-wheelers, we use BLDC.
Okay, sir.
Okay, I hope this might be a very informative session for you guys. Okay, any final note before leaving the session?
So the performance characteristics of DC machines are good according to the needs of the vehicle, sir. But due to high maintenance, it is not used. It is
Exactly. In DC machines, since you do not have any sinusoidal thing or any square wave, you will not have any such harmonics losses, as well as you are eliminating the requirement of power electronics converters, which is a huge thing.
yes,
Because
sir.
maintaining, you are eliminating the need of control, because control will be very simple in DC machine. You are eliminating power electronics converters, so your DC machine is very good in that perspective. But it's
Okay,
just
sir.
that maintenance is such that it is not able to cater, and your armature MMF is on the rotor. So if you rotate it at high speed, your armature will have the tendency to go out of the slots. So that mechanical perspective, that's another issue with DC machine. So we ideally want that a stator winding or armature winding should be on a stator winding, and we identify a stator winding as an armature winding. See, this is so widespread that armature winding we generally infer it to a stator winding, but in DC machine, armature is placed on rotor. So that is why
Okay.
DC machine is becoming slowly obsolete. But it can return if someone can do such invention that you remove the or you make such a good brushes and commutators such that it will solve all the existing problems. Then yeah, DC machine will be very good to operate. Okay, so any other further doubts?
No, sir.
No. So I think it's time to wind up the session. Okay, thank you very much, guys, for attending.
Okay, sir. Thank you, sir.
Thank you, sir. Thank you so much, sir.
Thank you, thank you. You are welcome.